Okay, hello everybody. My name is Henri Heinonen and I am from the University of Jyväskylä, Finland. I am a doctoral student in IT and my research area is blockchain technology. The topic today is blockchain-based decentralized microgrid energy distribution systems. So, what is an electric grid? It is a fully connected network where even small villages need to be connected to the main provider, and maintenance costs of such a network are usually very high. Due to that, around 70% of electricity bill consists of taxes and transfer costs. The remaining part, 30%, is the cost of the electricity itself. For example, one electricity provider has 230 meters of overhead power cabling per customer. And you can see the overhead power cabling here. In big cities, there could be dozens of meters of ground power cabling per customer. A small village with 50 to 200 households could have its own microgrid disconnected from main power grid. Combining blockchain technology with renewables, batteries and small nuclear power plants could provide cheaper electricity for microgrid users. In this presentation we describe novel blockchain-based energy distribution system. It allows regular individuals to participate in energy generation and distribution. We describe architecture of the system and provide economical justification of its usage. In addition to that, we compare electricity costs in such a system versus traditional distribution system in Finland. So what is the motivation for all this? The motivation number one is the climate change. According to California's Energy Future, the View to 2050 summary report shown here, California can achieve emissions roughly 60% below 1990s levels with technology we largely know about today if such technology is rapidly deployed at rates that are aggressive but feasible. And the summary report, it suggests these 4 key actions. These key actions can feasibly reduce California greenhouse gas emissions by 2050. Action point number 1 is aggressive efficiency measures for buildings, industry and transportation to dramatically reduce per capita energy demand. Key point 2 is aggressive electrification to avoid fossil fuel use where technically feasible. So I guess it basically means that you will still need to use regular fossil fuels in airplanes, but maybe electrification of cars is possible. So key point number 3 is decarbonizing electricity supply while doubling electricity production and developing zero emissions load balancing approaches to manage load variability and minimize the impact of variable supply for renewables like wind and solar. This is very interesting because zero emission load balancing, it basically means the nuclear power. And also in the bold letter you can see renewables like wind and solar. And also the key point number 4 is decarbonizing the remaining required fuel supply where electrification is not feasible. Motivation number 2 is distribution of electricity is expensive. Electric grid is a fully connected network where even small villages need to be connected to the main provider. Maintenance costs of such a network are very high, especially if distances are very long. Due to that, in Finland it is possible that around 70% of electricity bill consists of taxes and transfer costs. The remaining part, around 30%, is the cost of the electricity itself. A small village with 50 to 200 households could have its own microgrid disconnected from main power grid. Combining blockchain technology with renewables, batteries and a small nuclear power plant could provide cheaper electricity for microgrid users. Solar photovoltaics power and wind power are renewables that can generate electricity but not heat. The solar PV power, wind power and batteries are for regular households to generate, store and distribute clean electricity for the neighborhood through the microgrid. Here you can see the solar panel, the wind power plant and the Tesla's Powerwall battery. For storing electricity. So here you can see a nuclear power plant, a molten salt reactor, which is a generation 4 nuclear power plant. And they should come by 2020s or 2030s, I think. Nuclear power can produce both electricity and heat. It can provide clean and stable baseload electricity and also district heating. It is soon becoming a form of renewable energy source because uranium in seawater is basically inexhaustible, and the uranium extracted from seawater is replenished continuously, and because the price of extracting uranium from seawater shall become economically attractive soon. So what is a blockchain? Well, there are 3 kinds of blockchains: public, private and consortium blockchains. Bitcoin, Litecoin and Ethereum are famous examples of public blockchains. Everybody can join them by downloading the software and connecting to the network. Private blockchains are only open for users who have gotten the permission from the administrator, usually a company or organization. Consortium blockchains are hybrids combining features from both public and private blockchains. A blockchain is a tamper-proof distributed ledger. It stores transactions data in blocks. And usually proof of work is being used as a consensus mechanism, and those proof of work blocks are generated by mining nodes. Valid blocks are appended to the blockchain, and they will always use a hash pointer to refer to the previous block in the chain. The first block, the Genesis block, is a special block that does not refer to anything. Here you can see the hash pointer to the previous block. And here are the transactions, their hashes, and those hashes are also hashed together many times, and then it will be stored in the block. It is known as the Merkle root. So what is a smart contract? A smart contract is an application that is run in a distributed network. A very simple smart contract might work like a vending machine. User puts in a coin, the vending machine gives the user a candy bar. In Ethereum network's virtual machine, smart contracts are Turing-complete applications. They are usually written in Solidity language. Bitcoin has simple script language to write smart contracts that are not Turing-complete. The University of Jyväskylä's blockchain laboratory got a funding of €100,000 in 2018 for studying the development of projects applying blockchain technology in supplying of electricity. The duration of this Business Finland project's co-creation phase was 6 months. So let's get into the architecture of the system we are describing. According to this new research paper here, it can be very expensive to complete a trade in an electricity market on the public Ethereum network. Proof of work block mining is also consuming lots of energy. Our solution is to use private Ethereum network with proof of authority consensus. Private Ethereum network nodes do not need to download hundreds of gigabytes of historical Ethereum transaction data. Proof of authority uses identity as the sole verification of the authority to validate, and there is no need for mining blocks as in proof of work consensus. The blockchain and distributed ledger technology in general introduce new ways to pay energy bills. For example, one can use cryptocurrencies like Bitcoin, Litecoin and Ether to buy products and services. Our solution is to use trust lines network or Ripple concept to settle debts between electricity prosumers and consumers. For example, Alice here and Bob here are neighbors and they trust each other. Bob, prosumer, has batteries and solar panels and wants to sell electricity. Alice, consumer, only wants to buy electricity. Alice gives Bob an IOU worth of $5 and Bob gives Alice electricity worth of $5. A smart contract between Alice and Bob is created about the electricity purchase. Here's the transaction of the agreement between Alice and Bob, and then it will be broadcast to the network. All the other nodes in the network will validate the transaction and the purchase will be added to the blockchain. And it will basically be there forever because information is not removed or edited in the blockchain. Let's make several assumptions of our small village example. There are 3 households and 9 residents in the village, a small nuclear power plant and a small wind power plant. The nuclear fission power plant can generate around 84 kilowatt-hours per day. For comparison, the experimental nuclear fission powered satellite SNAP-10A that was launched in orbit in 1965 by USA could generate around 12 kilowatt-hours of electricity per day. Let's also assume the wind power plant can generate slightly over 14 kilowatt-hours per day. Alice is living with her family. They have a 4-person household. Charlie is also living with his family. They have a 4-person household. Bob is living alone and he has a battery pack and 10 pieces of 275 WP solar panels that can in total generate around 6.5 kilowatt-hours per day in average. let's make these assumptions for the price levels. These are just artificial price levels for this village example. The price level for electricity from nuclear power is 0.06 euros per kilowatt hour. The price level for electricity from wind power is twice of the nuclear power, 0.12 euros per kilowatt hour. The price level for electricity from PV solar power is twice the price of wind power, 0.24 euros per kilowatt hour. Let's also assume the energy mix to be 80% nuclear power, 10% wind power and 10% PV solar power. Alice's household needs almost 51 kilowatt hours per day. The same is true for Charlie's household because they are of the same size. Bob only needs slightly less than 4 kilowatt hours per day, and he wants to sell all his solar electricity to Alice and Charlie because Bob wants to make some money with his solar panels. At least he wants to get back the price he had to pay of those panels. And here we can see a list of energy consumptions and costs of households. So Alice has to pay less than €1 from the solar power to Bob and less than €1 to the wind power station, and slightly over €2 for the nuclear power, and same for Charlie. And Bob doesn't want to pay of his own solar energy. He wants to give all the solar power to his neighbors. But of course Bob is also using electricity, so he will use the wind and nuclear power. And here is the trust line network of the microgrid system. Here is Bob with solar panels, and there's the nuclear power plant, and the wind power plant is here. Alice is here, and Charlie's household is here. As you can see, for example, Alice, all those arrows are going from Alice, so it means that she needs to pay some money to get the electricity. He pays money to Bob to get solar power. He pays money to the nuclear power plant to get some nuclear power, and she also pays money for the wind power plant to get some wind power. And same goes for Charlie. Bob only pays for the nuclear power and wind power. And here are some calculations. As you can see, Alice and Charlie, they are not generating anything, so they are not getting any income from the electricity. They are just consuming electricity, so they have to pay for it. But Bob is also generating some electricity, so it seems that it's possible to get more money out of it than what is used for the electricity itself. So Bob is getting slightly over €1 per day after his own electric bill. So basically this means that Bob will eventually get back of the investment that he put in the solar panels. And of course the wind power plant and nuclear power plant, they are also getting some income. So in summary, in Finland, according to Helsinki Energia, Bob would have to pay around 6,100 euros for the 10 solar panels that will produce 2,370 kilowatt hours per year in total. With the electricity price level of 0.063 euros per kilowatt hour, it will take about 41 years for the panels to produce enough kilowatt hours to justify the panel cost. And this for the 10 pieces of 275 VP solar panels. And this is probably the number in Finland, that much solar power you will get in Finland per year. So over 40 years, that's a long time. I think the solar panels won't even last for that long. I think our small example shows that it might be feasible to use blockchain technologies on a microgrid that consists of renewables, batteries, and a small nuclear power plant in a way that is economically justified. And here you can see the references. Thank you. Please see our webpage for information on our blockchain laboratory. You can also contact me by sending email to my email address seen here. Thank you. And please also send some comments on my YouTube video. Bye.